My topic this afternoon is the history of chemistry between 1914 and 2019. This might seem a strange period, but it partly connected to a series of volumes which has just been published, The Cultural History of Chemistry by Bloomsbury Academics. And I was one of the general editors, which is Alan Rock in America. And there are 6 volumes altogether, as you might guess from what I've just said. They start with the ancient Egyptians and ancient Assyrians, and start a little bit later, the Greeks and Romans. That's in the first volume, and then it goes all the way up to the sixth volume, which deals with this more or less long century between 1914 and 2019, of which I was the volume editor, to be specific. This talk is based on the introduction to this book. As I converted it into a talk, I realized that it covers the topic can seem rather superficial. So excuse me while I let some more people in. May seem rather superficial, but there's no other way of dealing with a who topic in 45 to 50 minutes, and I'm afraid maybe even a bit longer, so apologies for the length of it. But I hope, although some parts of the talk will be new to you, even though others are familiar. Next time, I will talk about the history of the chemical industry in the 20th century, and that will be a bit more in depth and perhaps a bit more novel to everyone, apart from maybe a few people who worked in the chemical industry. Now, in 1916, to be precise, Easter 1916, in the midst of a massive international conflict, which is sometimes called the Chemist War, along with an ill-fated uprising in Dublin, the Dyson Perrin Laboratory opened its doors for the first time in South Park Road, Oxford. The building was the brainchild of William Henry Perkins, Jr., the Hugh Wainfleet Professor of Chemistry at Oxford, who firmly believed in the importance of research in chemical education. By coincidence, it was also exactly 60 years since his father, William Henry Perkins, made the first synthetic coal-tar dye mold in the East End of London, thereby creating an entirely new branch of the chemical industry. The DP, as it was always called, was the latest iteration of a style of laboratory building pioneered by the German chemist August Wilhelm Hofmann in the 1860s. Yet, if one of the older chemists working in the chemical research laboratory, which opened across the road from the DP in 2004, had been magically transported back to 1916, they would have found much of the interior of the building familiar. So does that mean that chemistry hasn't changed since 1916? Hardly. In many other ways, chemistry has changed much more since 1916 than in any other period of 100 years. There are now far more chemists than there were in 1916, you may have noticed, and they're much less likely to be white, European or American males, although, let's be honest, many of them still are. As a group, these chemists produce far more papers and write far more books than their predecessors. The actual content of the chemistry they carry out and write about is vastly more sophisticated than that of their 19th century predecessors. This is at least in part because of a much larger number of instruments they use and the much greater power of these instruments to probe compounds and reactions. Above all, although I won't be talking much about that, the use of computers have completely transformed chemistry in the last 40 years, as this diagram demonstrates here, where we have a protein structure shown in a way that's only possible by using computers, both to do the calculation and to create the display. So, what have been the major breakthroughs in chemistry in the 20th century? While the chemistry of century may lack a generally accepted revolution in chemistry, it certainly witnessed marked changes in the way that chemistry was both conceived and carried out. In particular, the introduction of the electron as a chemical as well as a physical entity at the very beginning of our period both transformed chemistry and unified the hitherto largely unrelated branches of inorganic, organic, and physical chemistry. This shift made possible the development of reaction mechanisms, both organic and inorganic, spectroscopy, transition metal coordination chemistry, electrochemistry in its latest manifestation, and solid-state chemistry. Scientists' improved understanding of both electronic bonding and the atomic nucleus led to the transformation of chemical instrumentation. Now, chemical reactions are truly at the heart of chemistry. I think we would hopefully all agree about that. And our understanding of reaction increased dramatically during the 20th century. The earlier part of this period saw the development of organic reaction mechanisms, which emerged from a combination of new understanding of chemical bonding based on electron and the increasing sophistication of chemical kinetics, particularly the measurement of the rate of reaction. Because without knowing the rate of reactions, you cannot discover or at least prove the mechanism. The mechanistic interpretation of chemistry was then extended to inorganic chemistry, most notably transition metal chemistry. The spectra of the compound and the geometry in space were now explained by a simplification of quantum chemistry called Ligand field theory. And on this slide, you will see a picture of Leslie Orgel, the English chemist who was one of the founders of Ligand field theory, although he later moved into astrobiology and the origin of life, a somewhat bigger topic. Once chemists had gained a solid understanding of chemical reactions, their focus switched to the more extreme cases, reactions that occur in a fraction of a second, and reactions between indeed individual molecules. This increased understanding of reaction has been underpinned by the development of theories of bonding between atoms, beginning with theories that simply dealt with the number of electrons in atoms, like Langmuir and Lewis, followed by models based on simple quantum mechanics, and finally, highly sophisticated calculations using computers. By the late 20th century, it was possible to demonstrate chemical bonding and reaction using computer graphics, as we've seen just a bit earlier. And our slide now shows to George Porter, who worked on ultra-fast reaction employing flash photolysis. If you were at our conference in December, you would have heard all about it. Now, if chemical reactions and chemical bonding are central to chemistry, and I think we would agree on that, the structure of chemical compounds are just as important because they make it possible to predict how a compound will react. At the beginning of our period, there was no way that one could actually see a chemical structure. One could only infer it from a compound reaction. And that's a very complicated business, needless to say. The first major breakthrough was the development of X-ray crystallography, which works, as you probably know, because X-rays have wavelengths close to the length of chemical bonds and roughly the size of atoms, and are therefore diffracted by crystals. The technique cannot actually determine the structure directly. It can only determine the position of atoms in a crystal, and believe me, even that is a complicated business and was made much simpler by the introduction of computers after the Second World War. The father and son team, William and Lawrence Bragg, applied this technique to crystals of inorganic compounds such as sodium chloride. As X-ray crystallography became more sophisticated, it became possible to surmise the structure of organic compounds from the indicated position of the atoms in their molecule. Kathleen Lonsdale showed in 1929 that hexamethylbenzene, and by implication benzene itself, were both flat and irregular hexagons. By the 1940s, X-ray crystallographers were able to work out the structure of penicillin before organic chemists could agree on its structure on the basis of its reaction. One of the leading X-ray crystallographers in the penicillin project was Dorothy Crowfoot Hodgkin, who went on to work out the very complex structure of vitamin B12 in 1956 before the organic chemist such as Lord Todd had any success with traditional methods. Awarded the Nobel Prize in 1964, she also worked on the structure of the large hormone insulin, which you may have heard about at our last online lecture last week. And that's a model of insulin that's in the Science Museum in London. It was in the National Portrait Gallery for a while on loan. Now, the chemists working on penicillin also used infrared spectroscopy and ultraviolet spectroscopy, which came into general use in the 1940s. However, these techniques were only able to show what kind of bond the compound had, not how the bonds were actually arranged in the molecule. So, in that respect, both X-ray crystallography on one hand and spectroscopy on the other had their limitations. The next major breakthrough was the development of nuclear magnetic resonance, NMR spectroscopy, in the 1950s, based on earlier work by physicists in the United States, and some of you may have been present when I gave my talk on NMR last year. As you probably all know, this technique uses powerful magnets and radio waves to tickle hydrogen atoms in organic compounds to find out how these atoms are arranged in the molecule. Now, this is the real breakthrough. The NMR could actually tell you which atom was next to whichever atom. By itself, however, the interpretation of NMR spectra of more complex molecules, at least, was still a matter of informed guesswork. But combined with ultraviolet and infrared spectroscopy, the structure of most organic compounds could now be worked out without the use of X-ray crystallography or resorting to the laborious study of the compound reaction. Additional help in analyzing a compound structure was soon forthcoming from another technique borrowed from physics, namely mass spectrometry. The mass spectrometer converts an atom or molecule into a charged particle or an ion, and then shoots it across a magnetic field which curves its path. The amount by which the path bends depends on the mass of the ion. Francis Acton at Cambridge was concerned only with the issue of isotope when he first built his first mass spectrograph, an early version of the mass spectrometer, in 1919, using it to show that neon and chlorine each had two major isotopes. Eventually, the technique became so sensitive that one could deduce the molecular formula of a compound from the very accurate molecular weight determined by a mass spectrometer. In the 1960s, chemists started to use the way that a compound actually breaks up within a mass spectrometer to gain additional information about its structure. In a way, it's almost like a reversion to the over method of using reactions, because these reactions were usually carried out to break up the compound. Initially, both NMR and mass spectrometry were used for relatively small molecules, the larger protein and enzyme molecules being left to the X-ray crystallography. And in the slide here, we have three of the early leaders of this attempt to try and work out the structure of organic compound from mass spectrometry: Carl Bayman on the left, Carl Dorassi in the middle, and Fred McLafferty from the Dow Chemicals on the right. Now, moving on. However, by the end of the 20th century, both NMR spectroscopy and mass spectrometry were being used routinely to study large biological molecules. Combined with the use of computerized molecular modeling, these techniques revolutionized the study of large proteins around the turn of the 21st century, and in particular, the implications of protein folding for degenerative diseases such as Alzheimer's disease and Parkinson's disease. And in the slide, you can see the person who did the most to do that, the sadly lamented Chris Dobson, who died all too early. To sum up, all the physical methods taken together reduce the timescale for the elucidation of a complex organic compound from a decade or more, of patient investigation of myriad chemical reactions, to a few hours spent studying the output of these sophisticated and expensive machines. Now, a completely different approach to seeing atoms, and you do almost in one sense literally see the atoms here, is the tunneling the scanning tunneling microscope, STM for short, thank goodness, would make an ultraviolet metal tip travel over the surface of a metal or a semiconductor such as silicon to measure the electrical forces given off by the atom, and thereby to construct an image of its microstructure. STM was developed by Gerd Binning in the slide and Heinrich Rohrer at IBM Laboratories in Zurich in 1981, for which they were awarded the Nobel Prize in pretty rapid order in 1986. In the same year, Binning with Carven Quate and Christopher Gerber introduced atomic force microscopy, AFM, which is similar to STM, but detects the interatomic forces of the atom. Thus, AFM can be used with insulators as well as metal and semiconductors, thereby greatly extending the scope of the technique. But of course, it's very different from NMR and spectroscopy. It's a different line of business. Now, another key aspect of chemistry, which we haven't touched upon yet, is the analysis of materials and the separation of complex mixtures. The 1950s and 1960s saw the development of two methods which greatly increased the sensitivity of analysis of the elements in the material, namely atomic absorption spectroscopy, AAS, which was a refining of the atomic spectroscopy introduced by Robert Bunsen and Gustav Kirchhoff as far back as 1859, and X-ray fluorescence spectroscopy, which is ultimately based on the work of Harry Moseley before the First World War, which is both non-destructive and extremely sensitive. The 20th century also saw the development of a very powerful method of separating mixtures, namely chromatography. Chromatography has many variants. You can see them on this slide here: partition or liquid-liquid chromatography, paper chromatography, thin layer chromatography, gas-liquid chromatography, and HPLC, which can variantly mean high-performance liquid chromatography, high-pressure liquid chromatography, or some people would have it high-price liquid chromatography. Now, the original form of chromatography, which involved passing a solution of a mixture down a column of powdered material, which technically is liquid-solid chromatography, was introduced by the botanist Mikhail Schwedt in the early 1900s. He called it chromatography, which means color writing, because he was using it to separate mixtures of plant pigments, which produced color bands in the column. Schwedt died aged 47 in 1919, and his technique language into the English chemist Arthur Martin had the idea of loading the powder with a solvent beforehand, so that the separation took place in the liquid phase, in other words, like partition separation, rather than at a liquid-solid interface. He introduced this so-called partition or liquid-liquid chromatography with Richard Singe, who I might say was a past member of our historical group in the early 1940s. Martin and Singe then applied the technique to filter paper, thus introducing paper chromatography. Realizing that thin layers of silica on plates would be both more rugged and sensitive than filter paper, the American chemist Justus Kircher developed thin layer chromatography in 1946. Now, collaborating with Anthony James, a former president of the National Union of Students, you can't imagine a current president of the National Union of Students ever becoming an important chemist, but there you go. Martin introduced the very powerful technique of gas chromatography, more precisely gas-liquid chromatography, in the early 1950s. This procedure originally used ordinary glass tubing coated with silica, which was later replaced by metal tube packed with alumina or absorbent polymers. An inert gas, such as nitrogen or hydrogen, well, hydrogen is obviously not inert in some sense, but it is in this sense, carries the unknown mixture through the column. Gas chromatography was very useful for mixtures of relatively volatile liquids, for example, petrol. That meant that it was taken up with great enthusiasm by the petroleum refining industry, and both BP and Shell played an important role in the development of gas chromatography. The problem of detection was solved by the development of two highly sensitive detectors: the flame ionization detector, devised independently by Ian McWilliam in Australia and Victor Pretorius in South Africa, and the more sensitive electron capture detector by James Lovelock, who was at that time a colleague of Martin and James at the National Institute for Medical Research in Mill Hill, North London. And remarkably, he's still with us, although he's now over 100 years old. In the long run, however, the most important and most sensitive detector for gas chromatography, and HPLC as well, was the mass spectrometer. The mass spectrometer was combined with gas chromatography in the mid-1960s, and HSPLC was introduced a decade later. In the slide, you will see a good example of a very boring example of a GCMS system. These are known as hyphenated systems for the obvious reason. Using a mass spectrometer to detect at the end of a chromatographic separation not only allows identification of compounds from their precise mass, but also uses a stored library on computer of fragmentation patterns to confirm that identification. So it's incredibly sensitive, incredibly sensitive. Now, another important activity in chemistry is synthesis, the making of a compound from simpler compounds. In academic organic chemistry at the beginning of our period, synthesis followed the analysis of natural products. Hence, synthesis follows analysis. The prime purpose of this type of organic synthesis up to the 1950s was to confirm the structure of a compound surmised by chemists from the results of a degradative reaction. As the chemist could never be certain if the hunch was correct, and it was really no more than a hunch, these degradative reactions sometimes did not take the expected pathway. When we think about rearrangements like the Wagner rearrangement, the final synthesis was a key part of an entire time-consuming, decade-long process. When the process of determining the structure of organic compounds was transformed by physical methods that we have seen in the 1950s, academic organic chemists then had to find a new rationale for organic synthesis. It became a challenge of intellectual and experimental prowess, rather like mountaineering, and a testbed for new reactions. And we see in the slide Robert Burns Woodward, one of the most famous organic chemists of his time, who synthesized not only chlorophyll but vitamin B12. So, the space in which all these activities take place, namely the laboratory, and you may recall my talk on the laboratory a while ago now, has also changed in this period, not only as a result of the instrumentation, but also due to new health and safety legislation. On that topic, I might just mention that when I insisted on wearing rubber gloves in the DP, which we heard about earlier, in 1976, because I was worried about the amount of chemicals I was getting on my hand, there was absolute horror, and there was even suggested that they might ban it. I mean, goodness knows. Well, what about today, where you have to wear rubber gloves? I was the first one to do it, you know. While the expensive, heavy, and bulky instrumentation introduced by the chemical revolution needs space, they have largely taken over areas in the laboratory formerly occupied by an earlier generation of instrumentation. Spectrometers sit in rooms that would have perhaps been used as photographic darkrooms or for the atomic spectroscope. While the mass spectrometers and NMR machines are lodged in the basement because of their weight, which in older days would have been used for a really nasty combustion analysis. By contrast, death and health regulation now dictate that the handling of particularly hazardous materials, we mean practically all materials, take place in fume cupboards, which now dominate laboratories as we see in this picture of a new chemical laboratory at the University of Aachen at Dulwich, taken from Wikipedia. Hello. Now, as it's no longer even permitted to eat and drink or write up research reports in laboratories, glass walls now often separate laboratories from the offices in which these permitted activities now take place. Now, the 20th century has also seen the development of entirely new self-disciplines, as this list here shows, and like it or not, I'll be going through all of them. A very important early example of these new fields was polymer chemistry, founded by the German chemist Hermann Staudinger in the 1920s. In this period, most chemists assumed that compounds that seemed to have improbably high molecular weight, such as rubber or cellulose, were in fact loosely bound aggregates of smaller molecules which were often considered to be ring compounds. Because otherwise, what do you do with the ends? Staudinger argued, by contrast, from what might be described as a conservative viewpoint, that rubber and cellulose consisted of actual molecules, he called them macromolecules, which were very large, but nonetheless still behaved in the same way as small molecules. Incredibly controversial at the time, strange though it may seem now. As a result of X-ray crystallographic studies of natural polymers, two other German chemists, Hermann Mark, who was actually Austrian, and Kurt Meyer, gradually accepted Staudinger's thesis. The work of Mark as a physical chemist and Staudinger as an organic chemist brought together the polymer revolution, as you might call it. It's not insignificant that Mark at that period worked for the German chemical compound IG Farben. Two other major contributors to the polymer revolution were also working in industry, namely Wallace Hume Carruthers, who worked at DuPont and developed nylon, and his young colleague Paul Fleury, who then eventually went back into academia. And our slide this time shows Hermann Mark, who also lived to be about 100. Now, one new branch of chemistry which has strong links with physics is solid-state chemistry. It arose from the study of phenomena on the surface of solids, chiefly with the aim of understanding catalysis on one hand and the development of transistors on the other. A major theoretical breakthrough was the phase diagram based on Gibbs phase rule of 1878, but not introduced until about 1919. Initially used in metallurgy, it became the basis of much of solid-state chemistry, which is concerned with surface reactions and the properties of bulk solids. An early pioneer of solid-state chemistry was Erwin Langmuir, who was awarded the Nobel Prize in 1932 for his work on surface chemistry while he was at General Electric. Incidentally, when I was young, Erwin Langmuir was regarded as a great hero of chemistry. How do you ever hear about him now? The development of solid-state chemistry was accelerated by the introduction of differential thermal analysis, in which the heating or cooling of a sample was measured against an inert reference material. This technique was partly displaced by differential scanning colorimetry, introduced in 1964, and they were both eventually displaced by thermogravimetric analysis. Now, it was from solid-state chemistry that the new discipline of materials science rose in the 1970s. One important root of this discipline was metallurgy, and which has existed as a scientific subject since the mid-19th century. And this discipline was revolutionized by the application of solid-state physics, in particular X-ray diffraction and the use of quantum theory, since the 1940s. At the same time, the more recent field of molecular chemistry or polymer chemistry began to apply their method of physical chemistry, partly because of the work of Hermann Mark and Paul Fleury, and indeed even physics, to the study of macromolecules. With hindsight, it may seem surprising that these two fields, metallurgy and macromolecular chemistry, took so long to find a common ground in the new materials science. But one should never underestimate the power of disciplinary inertia. Since the 1970s, the material-related sciences have been combined at both the institutional level and intellectually, while still retaining a strong sense of own identity. Now, when it came to deciding whose picture to put on this particular slide, material sciences, I had a good long hard think about it. And in the end, they decided who could it be better than John Goodenough. After all, he's good enough. No, sorry, pardon me. I chose him because he practically came from physics, but he became professor of inorganic chemistry, which seems highly surprising unless you realise that inorganic chemistry at Oxford in the 1970s was very much solid-state chemistry. Didn't really tackle there. He taught me, didn't understand a word of what he was saying, which was about Fermi gases and conductivity. But while he was at Oxford, he set into motion the work that he was doing, which ultimately led to the lithium battery. So most of you are watching this lecture as a result of the research carried out by John Goodenough, and of course he's now a hero of material science. And now another new field that was introduced with much hope and hype in the 1980s was nanochemistry, the concept that one could manipulate and assemble molecules at the atomic or nanometer level. It became a useful umbrella term for techniques such as STM and AFM, and new fields such as supramolecular chemistry and the following. An early example of nanotechnology hype was the spelling out of IBM using 36 xenon atoms on a nickel surface in 1989, which you can see on the slide. It actually becomes more obviously IBM if you try and look away from the screen rather than too close to the screen. It's not so obvious when you're really staring at the screen. Buckminster Fullering, named after the American architect Buckminster Fuller, who otherwise had nothing to do with it, is a molecule composed of 60 carbon atoms in the shape of a soccer football. It had been predicted, entirely tongue-in-cheek, by the scientific satirist Daedalus, David E.H. Jones, in 1966, and more seriously by A.J. Osawa in 1970. But it was first produced in the laboratory by Robert Curl, Howard Kroto, and Richard Morley in 1985, for which they were awarded the Nobel Prize in 1996. ITM method for the manufacture of gram-sized quantities of C60 was developed in 1990. There was much excitement about the potential uses of buckyballs and its chemical relative to fullerene and carbon nanostrips. In 2004, the Russian-British physicist Andrei Gain and Konstantin Novoselov produced a monoatomic layer of graphite. Graphite, for which they call graphene, simply by peeling a piece of tape off a stick of graphite. In fact, you can even do it with a pencil, I believe. They were awarded the Nobel Prize in 2010. However, many of the expectations associated with all these new materials remain largely unfulfilled even today. The living organism can carry out numerous complex reactions under mild conditions of room temperature. For over 2 centuries, chemistry have admired this ability while struggling to reproduce it. During the 20th century, chemists discovered reactions would take place under such benign conditions. For example, the synthesis of tropinone by Robert Robinson in 1917. You see him on that slide, but they're relatively uncommon. Nature succeeds, but chemists fail because it uses the three-dimensional environment to control the reaction through interatomic forces. It was the discovery of the so-called crown ethers by Charles Peterson at DuPont in 1967 that triggered interest in creating a specific three-dimensional environment for a given reaction without having to make the large complex protein used by nature. Jean-Marie Long have made three-dimensional analogues of Peterson's crown ethers in 1969, the so-called supermolecules, and was able to use them to distinguish different ions or to carry out chemical reactions to create a specific three-dimensional product. You can see him on the slide. The ultimate aim of this line of research is to create a three-dimensional chemical environment in which different molecules are allowed to enter and combine automatically to produce larger molecules, in the same way that nature uses relays of enzymes. Today, supramolecular chemistry includes molecular devices and machines, molecular recognition, and processes such as self-assembly and self-organization. Synthetic or artificial enzymes having the characteristics of supramolecular chemistry have been developed to provide catalysis with rates and selectivity that approach those of natural enzymes. Chemists have also produced polymeric supramolecules. Another approach is to use synthetic geolites, which are porous material containing aluminium, silicon, and oxygen, with specific pore sizes to influence selectivity and speed up reaction in a similar way. In the 19th and early 20th century, there were various forms of medical chemistry, and many chemists worked in laboratories and hospitals. By the way, can I just say, I can't really see, no, please put any questions you have in chat and I'll deal with them after the lecture. So, organic chemistry itself had arisen from the study of the products of the human body, animals, and plants. In the 1920s and 1930s, these overlapping fields left chemistry and medicine to become biochemistry. This was a new discipline, separate from chemistry in the USA and Britain. However, in continental Europe, it was still considered to be a subdiscipline of chemistry alongside organic chemistry and inorganic chemistry. Biochemistry was strongly supported by the Rockefeller Foundation in the United States, but hindered in Germany by the rigid disciplinary division in German universities. It is nonetheless a testament to the strength of the field in Germany that major advances were made there by Otto Warburg and Hans Krebs. Hans Krebs elucidated the metabolically important urea cycle in Germany, and after he emigrated to Britain in 1933, he discovered the even more significant citric acid cycle, which in my youth was always called the Krebs cycle, but nowadays it seems to generally be called the citric acid cycle, and we can look at it here. I don't know if any of you remember the posters that Cox Light Laboratories in somewhere west of London, Basingstoke, somewhere like that, used to produce, but showed how all these different pathways were sort of interlocked. I never really understood them, but they looked fantastic on a student bedroom wall. Now, despite the success of biochemistry, it was soon overshadowed by the discovery of the structure of DNA by a combination of physicists Francis Crick and Maurice Wilkins, a biologist James Watson, and a chemist Rosalind Franklin, rather than biochemists. Thus arose the new field of molecular biology, with its subsequent successes in genetics. Up to almost the end of the 20th century, biochemistry and molecular biology appear to be drifting away from chemistry. But a renewed interest in large biomolecules by chemists has partly brought these boundary disciplines back under the umbrella of chemistry. And in this slide, you can see a partial view of a DNA molecule, DNA model made using some of the steel plates used in the original model at the Laboratory of Molecular Biology in 1953. Some of you will know that famous picture where Crick and Watson are standing next to the model, and Watson is pointing at it with a, I think it was Watson who was pointing at it, with a slide rule, a rather fashioned piece of kit. I would have shown a picture of Rosalind Franklin, because frankly, I'm very embarrassed by the number of men I'm showing compared with women. You will see a few in a minute. But I could not get an image which was free to use. And the trouble is, now we're recording these talks, and I hope I'm recording them. I'm recording these talks and putting them on the web. It's become more difficult to use sort of not free to use images. I'm afraid I don't have an image of Rosalind Franklin as much as I would have liked to have done. Now, moving into yet a different field, geology and mineralogy have always had strong links with chemistry. For example, the discovery of many elements, notably the rare earth found in the rocks in the mine at Göteborg near Stockholm. The development of a subdiscipline of geochemistry was the result of the interest of certain mineralogists and chemists in the relative abundance of the elements on the Earth's crust on one hand, and the development of X-ray techniques on the other. The pioneer of modern geochemistry was the Norwegian mineralogist Victor Goldsmith in the 1920s and 1930s. The technique of radioisotope abundance arises from the concern with elemental abundances as radioisotopes decay over time and that allow the dating of rocks and other materials. For example, the decay of potassium-40 to argon-40 allowed the relatively accurate determination of the age of the Earth's oldest rocks, and indeed less old rocks, in the 1960s. On an entirely different time scale, which is in that case billions of years, is the use of radioactive carbon-14 dating to calculate the age of organic materials before one part of the living system. This technique was developed by the American chemist Willard Libby, who you can see in the slide, in the late 1940s and 1950s, for which he was given the Nobel Prize in 1960. While geochemistry was initially much concerned with the abundance of the elements, which were found to be similar in both the Earth crust and meteorites, it later expanded into other fields such as biological geochemistry, which is the effects of organisms on the Earth's chemistry, and organic geochemistry, the study of organic compounds in rocks, which was particularly associated with Geoffrey Eagleton in Bristol. Now, up to the mid-1920s, it was assumed that the stars had the same elemental abundances as the Earth, but it was then shown by Cecilia Payne, who had once been head girl at St. Paul's Girls' School, that the Sun and other stars were composed mostly of hydrogen. Once the Big Bang theory was introduced in the 1930s, many scientists assumed that all the elements had been created during the cooling of the universe immediately after the Big Bang. However, astronomer Fred Hall, who opposed the Big Bang theory, showed in the mid-1940s and early 1950s that the heavier elements were formed in the stars themselves or in supernovae, which are massive stellar explosions at the end of the star's life. This line of research culminated in a famous 1957 paper by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hall on stellar nucleosynthesis, a paper familiarly known as B-squared FH. And in the slide, you can see Geoffrey Burbidge, Margaret Burbidge, and William Fowler, but not Fred Hall. Then attention turned to the detection of organic chemical molecules in space, aided by the development of radio astronomy. Most of the earlier chemical species discovered in interstellar space were diatomic, molecular hydrogen, for example, and it was assumed that larger molecules would be torn apart by UV rays and cosmic rays produced by stars. This assumption was undermined by the detection in space of the tetraatomic molecule ammonia by Charles Towne, more famous for being the inventor of the maser, in 1968. A year later, the first organic molecule in space, namely formaldehyde, was detected by the Green Bank Radio Telescope in West Virginia, which sadly collapsed in November 1988, as you can see in this rather sad picture here. Since then, a cosmic zoo of chemical molecules have been detected both in interstellar space and in heavenly bodies such as comets and asteroids, including such exotic species as Buckminsterfullerene, bentonitrile, and even the argonium, which is ARH+, which was detected in the Crab Nebula, which is a supernova remnant in the constellation of Taurus, which is in the picture there, taken by the Hubble Space Telescope in 2013. Almost purely by accident, I believe. Now, it is striking that most governments around the world have sought to increase the number of chemists in their countries during the 20th century. This was partly because of the economic benefits they presumed would accrue as a result of having more chemists working in industry, but also because of the value of chemistry teachers and researchers in the field of medicine. More recently, in professional organisations have sought to increase the number of women and ethnic minorities in higher ranks of the chemical profession. Already, almost as many men as women are taking first degrees in chemistry in many Western countries, although women were still a small minority of graduates as late as the 1970s. The problem has mainly been enabling women to rise higher up the ranks, and a recent example of that is Professor Yellowlees from the University of Edinburgh, who would have become a president of the RSC a few years ago. So things are beginning to change in some countries more than others. Now, the professional organisation of chemistry has been expanded in the last century alongside the expansion of chemistry itself, as shown in this table. The merger between the Chemical Society and the Royal Institute of Chemistry, along with two smaller organisations, the Faraday Society of Physical Chemists and the Society for Analytical Chemistry, to form the Royal Society of Chemistry, took place in stages between 1972 and 1980. Similarly, Germany had two chemical organisations before 1946, the Deutsche Chemische Gesellschaft, which was modelled by Hoffmann on the Chemical Society, founded in 1867, and the Verein Deutsche Chemiker for applied chemists, similar to the Society for Chemical Industry, founded in 1877. They merged to form the Gesellschaft Deutsche Chemiker, which means the Society of German Chemists, in 1949. Now, if you look at the table here, and I'm not going to go into it in great detail, you will see a rather striking phenomenon. So the American Chemical Society has grown 21 times since roughly 1914 to 2018, and we haven't done badly either. The two British Chemical Societies have increased from 4,500 in 1914, although of course that probably includes a good deal of double counting, to 54,000 in 2018, that means it's expanded at least 12 times and probably even more than that, perhaps even as close to the American 20 times or so. By contrast, Germany and France have only grown by about 3 or 3.5 times. Now, it's a very interesting phenomenon, and I'm not entirely sure of the explanation, except, of course, America has become phenomenally important in chemistry. Now, on the international level, the International Association of Chemical Societies was founded in 1911. But it became a sad victim of World War I. Its successor, the International Union of Pure and Applied Chemistry, or UPAC, as it's always called, was established in 1919, although chemists from the Central Powers of Germany and Austria were initially excluded, and science chemists from the Soviet Union were also absent. German and Austrian chemists were invited to the UPAC conference in 1928, after Germany had been accepted into the League of Nations in 1926, and these countries and the Soviet Union became members of our UPAC in 1931. However, Nazi Germany was barred during World War II, and eventually East and West Germany became separate individual members of our UPAC. And of course, once again, later on, after 1989, they became one member again. Now, another important and well-known feature of the 20th century has been the global spread of chemistry. At the beginning of the century, although academic chemistry existed in most countries to a lesser or greater degree, it was largely concentrated in Europe and the USA. During the first half of the 20th century, leadership of the field, if we can define such a thing, moved from Germany to the United States, a result mainly of the policies of the Nazi regime in Germany between 1933 and 1945, but also partly because of the rigidity of the German academic system, and, on the other hand, the growth of petrochemicals and pharmaceuticals in America. The Soviet Union also became an important player in chemistry, but its achievements were hidden from general view in the West, partly by the use of the Russian language and the Cold War, and the special services were set up to translate Russian literature. Nonetheless, the half-century between 1950 and 2000 was one of almost rival superiority for the United States. Not only did its chemical and pharmaceutical industry undergo rapid expansion, and its chemists made major breakthroughs, including Nobel Prizes along the way, but many students and researchers were attracted to Britain, America, including a notable Bain Dane from Britain. Now, when it came to the question of who I should put on this slide, I thought long and hard about it, and I decided in the end that there was surely nobody more appropriate for the superiority of American chemistry than James Bryant Conant, who's shown in this picture in a relatively early slide of 1932, image of 1932. I chose him not only because of his achievement as a chemist, or even his achievement in reforming Harvard University, but because he became the he became the U.S. High Commissioner for Germany in 1951, 1952, I think to be precise. And so for a short while, he was practically the ruler of Germany. So what greater indication of the superiority of American chemistry if you have an American chemist virtually ruling Germany, or at least West Germany, or at least the American zone of West Germany, but then that's a large part of West Germany. He also was one of the sort of founders of the Kuhnian school of scientific revolution, since he was a great influence on Thomas Kuhn. So he had an important influence on the history of science as well. So by the end of the 20th century, East Asia were beginning. Japan gained the first Nobel Prize in Chemistry in 1981 to Kenichi Fukui, but its profile was very considerably by the award of no less than 5 Nobel Prizes between 2000 and 2010, as you can see on the slide here. In the 1980s and 90s, with the opening up of China, there was a steady flow of Chinese students into American universities. But by the 2000s, by the turn of the century in other words, they were beginning to graduate in notable numbers from Chinese universities as well. There's an increasing number of publications from Chinese universities, and there was an effort underway in the late 2010 to increase the quality of chemical research carried out there, although with rather unfortunate results from one chemist at Harvard. While American leadership of the field has remained almost unchallenged, China may be in a similar position to the United States at the beginning of our period in 1914. If anybody's still around at the end of this century, they will know the answer to that. So we have 2 Japanese Nobel laureates here, Kenichi Fukui and Georgi Niori. And you'll be pleased to know that we'll now come to our final slide, chemistry of the future. It could be argued that chemistry suffered an existential crisis towards the end of the 20th century. Several chemistry departments in the UK were closed down or became heritage science or forensic science departments, and many departments in the USA changed their name to molecular sciences. An increasing number of Nobel Prizes were being awarded to scientists who were clearly not chemists. The Nobel Prize in Chemistry were being awarded to scientists who were clearly not chemists. Will chemistry survive as a single discipline, or will it break up into fragments which will be absorbed by material science or physics and a large chunk by biomedicine, thus returning much of chemistry to its medical roots in the 18th century? But in the end, this did not happen. By casting its net wider, and by, in particular, reabsorbing much of biochemistry, chemistry has survived and has arguably become even larger. The major chemical organizations such as the American Chemical Society and the Royal Society of Chemistry appear to be confident that chemistry will continue to thrive in the 21st century. However, and this is my final word, as I have argued before in these talks, the chemist of the future may well indeed be a robot. And there's a picture of a robot from working in the laboratory in chemistry world. So chemistry may survive, chemists may not. Thank you very much for listening to the talk, and I hope you enjoyed it, and I hope you will stay the course and come back to hear me talk about the history of the chemical industry, which, as I say, will be somewhat more detailed and, dare I say it, even more exciting in a month's time. After which, if there are enough people watching this, and I do hope you will continue watching this, and I hope it's interesting enough that you will continue to watch this, then we'll have 2 talks on the 19th century, one in May and the other in June. And if we have enough people watching it by the end of that, we will proceed into the 18th century and back into the 16th century and the Middle Ages. Who knows? One day, next year, we may even reach deacency Egyptian. So once again, thank you very much for coming along. Thank you very much for attending. Sorry about the slight delay at the beginning, and I look forward to answering your questions. And I see there's one comment in chat, or two comments now want to come in. Thank you. Thank you very much. Thank you. Well, lots of nice thank yous there, and always greatly appreciated. If there are no questions, it's been a long talk. I've been gassing away for nearly an hour now, and I'll just wait another moment to see if there are any questions. I see you got him, Robert. Good job. Thank you very much, everybody, and I hope if you've enjoyed the talk, you will come back to the next one and keep this series going, because this is a series that will depend very much on people coming along. And I think we've had roughly 40 people today, so that's a good sign. So, once again, I wish you farewell. Have a good week. See you back for our next talk, which will be on the society, or no, will be on the discovery of elements predicted by Mendeleev by Mary Virginia Orner. That will be our very next talk in the middle of next month. In the meantime, I hope you keep well, and goodbye.